Section 2.6, two topics today. Topic 1, what is a continuous curve? Topic 2, what functions have continuous graphs? Now, topic 1. A curve is a continuous curve if it can be drawn without removing your pen from the paper. For example, this curve is not a continuous curve. Precisely, this curve is continuous everywhere except at this point. When you draw this curve with a pen, at this point, you have to remove your pen from the paper, then continue. A function is a continuous function if the graph of the function is continuous. Suppose this curve is the graph of the function f. Then the function f is not a continuous function. Precisely, this function is continuous everywhere except at point A. At x is A, the function is not continuous. Here are some examples about a function that is not continuous. You can find these examples in the book on this page. In this diagram, the function f is continuous everywhere except at a point A. At a point A, the function has a removable discontinuity. Why removable? Because if we add a point here, then the discontinuity is gone. In this diagram, the function f is continuous everywhere except at a point A. When we draw the graph of the function, at a point A, we have to lift up our pen, draw the solid point, then come back to draw the other part of the graph. In this case, the book calls the function f has a removable discontinuity at a point A. Because if we shift down the solid point here, then the discontinuity is gone. So this discontinuity is removable. In this diagram, the function f is continuous everywhere except at a point A. At a point A, the function has a jump discontinuity. In this last diagram, the function is continuous everywhere except at a point A. If we draw the graph of the function, at a point A, we have to remove our pen from the paper, then draw the other part of the graph. The book calls the function at a point A has an infinite discontinuity. Infinite discontinuity, just a name. More examples about continuity and discontinuity. Example 1, the graph of some function f is given below. In this diagram, we only plot the graph on the open interval 0 to 5. We only plot the graph between 0 and 5. Now, some questions. Question A, state the x numbers at which the function is discontinuous. B, for each of the numbers stated in part A, determine whether the function is continuous from the right, from the left, or neither. Question C, state the intervals on which the function is continuous. From the diagram, we can see that the graph is not continuous at this point, this point, this point, and this point. For example, when we draw the graph at this point, we need to remove our pen to plug this solid point. Therefore, the function f is not continuous at x is 1, x is 2, x is 3, and x is 4. At x is 1 and x is 2, the function has a removable discontinuity. At x is 3 and x is 4, the function has a jump discontinuity. Question B. For each of the numbers in part A, determine whether the function is continuous from the right, from the left, or neither. Let's consider the point 3 first. The function is not continuous at x is 3. But we can say more in detail. From this diagram, we can see that the function is continuous from the left side at the point 3 because there is a solid point here. The function is not continuous from the right-hand side at the point 3 because no solid point here, just open point, open point. Open point means the point is not part of the graph. Similarly, at point 4, the function is not continuous from the left side because there is an open dot here. But the function is continuous from the right side because solid point here. At point 1, the function is not continuous from the left side because open dot. Not continuous from the right side because open dot. At 2, the function is not continuous from the left side because open dot here. Not continuous from the right side because open dot here. Question C. State the intervals on which the function is continuous. From the diagram, between 0 and 1, the graph is continuous. The graph has no jump, no break. So the function is continuous on this open interval, 0 to 1. Between 1 and 2, the graph is continuous. So therefore, the function is continuous on this open interval. Between 2 and 3, the graph is continuous. At 2, the graph is not continuous from the right side, not continuous. But at the point 3, the graph is continuous from the left side. So the function is continuous on this half open, half closed interval. Open at 2, close at 3. Close at 3 means including 3. Between 3 and 4, the graph is continuous. At 3, the graph is not continuous from the right side. At 4, the graph is not continuous from the left side. So the function is continuous on this open interval. Now, the last interval. Between 4 and 5, the graph is continuous. At 4, the graph is continuous from the right side. At 5, the graph is not continuous from the left side. So therefore, the function is continuous on this half open, half closed interval. At 4, close. Close means including 4. At 5, the interval is open, excluding 5. Topic 2. In this topic, I want to answer this question. What functions have continuous graphs? The answer turns out to be simple. All the functions that we are familiar with, except some intentionally defined functions, are continuous everywhere on their domains. Namely, all the functions that we are familiar with, they have continuous graphs on their domains. Take a review about what is the domain of a function. The domain of a function is the set of x values where the function is defined or computable by a calculator. For example, the domain of square root of x is positive numbers and 0. Try with your calculator. If you plug in a negative number, say -1 in x, then your calculator will say that an error, not computable. But if you plug in 0 or a positive number in x, then your calculator is computable. The graph of square root of x is this curve. This curve is continuous everywhere on the domain, everywhere between 0 and positive infinity. Here is a list of the functions that we are familiar with. A, polynomials. We are familiar with polynomials. The domain of a polynomial is negative infinity to positive infinity. That is, a polynomial is computable at any number. B, power functions. We are familiar with power functions. X to A. A is a constant. For example, x squared, power function. X to the third, power function. X to 1/2, power function. X to 1/2 is square root of x. The domain of this function is any positive numbers and 0. This function is not computable at negative numbers. X to 1/3, 1/3. This is a power function. This function is cubic root of x. The domain of this function is any number from negative infinity to positive infinity. C, exponential functions. We are familiar with exponential functions. A to x. The base is a constant, different from power function. The power function is the base is a variable. Now, exponential function, the base is a constant. The power is a variable. Here we assume the base, a positive constant. For example, 2 to x is an exponential function. The domain of this function is any number. 1/2 to x is an exponential function. The domain is also any number from negative infinity to positive infinity. You can have a try with your calculator. Plug in negative number in x, 0 in x, positive number in x, and see whether or not your calculator can compute that number. Computable. D, rational functions. A function of a polynomial over a polynomial is called a rational function. Just like an integer over an integer, people call that number a rational number. This is a rational function, polynomial over a polynomial. The domain of this function is any number except 1. When you plug in 1 in this function, denominator is 0, not computable. In interval notation, the domain of this function is from negative infinity to 1, excluding 1, parentheses. Union together from 1 to positive infinity, excluding 1, parentheses here. E, trigonometry functions. There are 6 trigonometry functions: sine, cosine, tangent, cotangent, secant, cosecant. For example, sine. The domain of sine is any number between negative infinity to positive and positive infinity. You can have a try with your calculator. Arbitrarily pick a number. Then with your calculator, you can compute sine of the number. Tangent. Tangent is sine over cosine. The domain of tangent is any number, all the numbers, except pi over 2 plus k times pi, where k is any integer. Because at these numbers, cosine is 0. So the domain of tangent is all the numbers except these numbers. F, inverse trigonometry functions. There are 6 inverse trigonometry functions. For example, inverse sine. A second notation for inverse sine is asine. The domain of inverse sine is any number between and including negative 1 and positive 1. G, logarithmic functions. For example, natural log. Natural log, the base is e. E is a number, an irrational number. The number is 2.718 something. The domain of a natural log is any positive number. Natural log cannot take 0, cannot take negative numbers. A second example, common log. Common log, the base is 10. Again, the domain of a common log is any positive number. H, any function obtained by combining the functions above by summation, subtraction, multiplication, division, and composition is familiar to us. For example, a polynomial plus natural log plus a trigonometry function divided by a power function. We are familiar with a function like this. In these 5 operations, summation, subtraction, multiplication, division, and composition. Composition may be new to us. You can find a detailed explanation on composition on page 4 in the book. Here, let me show you some examples about this operation, composition. Let function f be psi, function g be 1 over x minus 1. Then f circle g is a new function. How to get this new function? Plug in g in the x here. Namely, this new function is f of g of x. Because g of x is 1 over x minus 1, so we have this equation. How to get f of 1 over x minus 1? In this equation, replace the 2x by 1 over x minus 1. Then we have this equation. This function is f composition with g. The domain of this function is any number except 1. When you plug in 1 in x, then you will get 1 over 0, log commutable. In interval notation, the domain is from negative infinity to 1, excluding 1, together 1 to positive infinity, excluding 1, parenthesis. Parenthesis means excluding. Now, g circle f. G circle f, this is a new function. This new function means this function, g of f of x. F of x is psi. Therefore, we have this equation. How to get g of psi of x? In this equation, replace the 2x by psi of x. Then we have this equation. The domain of this function is any number except these numbers, because at these numbers, psi is equal to 1. So 1 minus 1, denominator is 0 at these numbers. So the domain of this function is all the numbers except these numbers. Similarly, f circle f. F circle f means f of x. F of x is psi, so we have this equation. Now, how to compute f of psi of x? In this equation, replace all the x by psi of x. Then we get this equation. The domain of this function is any number. Finally, g circle g. G circle g, this function is g of x. Plug in this in g of x, then we have this equation. Then how to get this function? In this equation, replace all the x, all the 2x by 1 over x minus 1. Then we have this equation. Yeah. So g circle g is this function. Then what is the domain of this function? The domain is all the numbers except 1 or 2. When x is 1, plug in 1 in x, then 1 over 0, log commutable here. Plug in 2 in x, 1 over 2 minus 1 is 1. But then 1 minus 1, again, denominator is 0, log commutable. So this function, the domain is all the numbers except 1 or 2. This is the answer to this question. What functions have continuous graphs? About this answer, I have explained the domain of a function, and I gave a list of the functions that we are familiar with. Now, I explain what are intentionally defined functions. Take a look at these two functions. They are defined piece by piece. For function f, when x is 2, function value is 1. When x is not equal to 2, function value is x squared. The graph of x squared is a parabola. This function is defined at any number, so the domain of this function is from negative infinity to positive infinity. This is the graph of function f. The parabola is the graph of x squared. The parabola is continuous everywhere. Now, at x is 2, I intentionally shift this point on the parabola down to 1 to make the parabola not continuous at 2. So this function f, the domain is from negative infinity to positive infinity. But this function is not continuous everywhere on its domain. At x is 2, the function is not continuous. So this is one example of an intentionally defined function. Intentionally make the graph of the function not continuous. Function g is also an intentionally defined function. When x is greater than or equal to 2, function value is 1 minus x. The graph of 1 minus x is a 9. When x is less than 2, function value is x squared. The graph of x squared is a parabola. This function is defined at any number, so the domain of the function is from negative infinity to positive infinity. Now, I plot the graph of this function. From the diagram, we can see that the function is continuous everywhere except at the point 2. At the point 2, at x is 2, we intentionally make the function not continuous. Two more examples. Example 1. Determine the intervals on which the function is continuous. Then analyze the given limits. Recall that an intentionally defined function is a piecewise defined function. This function is not defined piece by piece, so this function is not an intentionally defined function. Therefore, this function should be continuous everywhere on its domain. Therefore, to determine the intervals on which the function is continuous, we just need to determine the domain of this function. The square root of x can take positive numbers, can take 0, but cannot take negative numbers. So the domain of this function is this interval. Therefore, the function is continuous on this interval. To find these two limits, we use direct substitution. X approaches 4, plug in the number 4 in x, then we get the limit is e to square root of 4 it is e squared. Similarly, to find this limit, plug in 0 in x, then we get the limit is e to square root of 0. It is 1. Example 2. Determine the intervals on which the following functions are continuous. These functions are not defined piece by piece, so they are not intentionally defined functions. They should be continuous everywhere on their domains. So to answer the question, we just need to determine the domains of the functions. To find the domain of this function, set the denominator to 0 and solve this equation by quadratic formula. Then we get x is 1 and negative 1/2. At these 2 points, function g is not computable or not defined because at those 2 points, denominator is 0. Therefore, the domain of function g is all the numbers except 1 or negative 1/2. In interval notation, the domain is the union of these 3 intervals. Therefore, the function g is continuous on these 3 intervals. The domain of this function is the union of these 2 intervals. At 0, this function is not defined because 1 over 0 is not computable. Therefore, this function is continuous on these 2 intervals. About this function has a square root of x. Square root of x cannot take negative numbers, so x must be greater than or equal to 0. Also, x cannot be 16 because square root of 16 minus 4 is 0. 1 over 0, the function is not computable. So therefore, the domain of this function is the union of these 2 intervals. So the function g, this function, is continuous on these 2 intervals.